Hi, I'm Erin, and today I'll present on mutational signature research. This presentation includes the following aspects. I'll start by introducing myself. I'm a rising junior at Lowndes High School in Georgia. I hold a leadership position in several clubs, including the Science National Honor Society, Science Club, HOSA, and the statewide American Red Cross Club of Georgia. I'm also founder and president of the Global Teen Medical Club. I am a USA Biology Olympiad semifinalist, and my research was recognized by several awards. I aspire to be a pediatric neurosurgeon. Mutational signatures are an emerging global health topic that has garnered significant attention in recent years. Let me talk about global health. Global health is about the health of global populations. It is the fundamental change in the terminology of international health. Global health is the area of research for achieving health equity. This presentation aims to elucidate why mutational signature research has become a critical global health issue. Mutational signatures are distinct patterns of genetic mutations, and they provide clues about the underlying biological processes. How? Let's consider cancer. Do you know how cancer develops? Cancer is a significant global health concern, and it's caused by mutations in genes. Each mutational process imprints a characteristic pattern of mutations on the tumor genome, which is known as mutational signature. Look at Figure A, which shows mutational signatures associated with tobacco smoking in human cancer. The pattern of mutational signatures is observed in tobacco smoker cancers in Figure B. For instance, in lung cancer, the tobacco-associated signature is typically characterized by a high frequency of C to A mutations. Therefore, mutational signatures enhance cancer prognosis prediction and potentially support treatment by revealing the cancer risk factors. This flowchart summarizes how mutational signature research proceeds. That is, when cancer is developed due to the mutational process, it imprints distinct patterns of mutations called mutational signatures. And researchers decipher those patterns of mutations and identify factors. This knowledge is crucial for developing effective prevention strategies and targeted therapies. Therefore, mutational signature research is critical, impacting disease etiology, personalized medicine, public health, and cancer research. Early cancer detection via mutational signature analysis enhances survival rates. However, limited research exists on the impact of age and sex on mutational signatures in pediatric tumors, hindering cancer prevention efforts. So my research aims to investigate the impact of age and sex clinical features on mutational signatures in pediatric tumors to understand cancer development across childhood age groups. I developed two research questions for my project regarding the association between the clinical features of age and sex with mutational signatures. I developed corresponding null hypothesis and the alternate hypothesis. My research was conducted through the following steps. First, I collected the whole genome sequencing-based TSV files from the ICGC data portal. The data consists of mutational signatures, of specimen histology, and of clinical information. Next, I grouped data by tumor type and the clinical features of age and sex. Finally, I analyzed mutational signatures in two compared groups, the childhood group, ages 13 to 17, and the young adult group, ages 18 to 49. I collected data using R and then analyzed data using the Wilcoxon rank sum test. I used box plots to visualize my data. The findings of my research demonstrated that the childhood group shows a higher frequency of somatic mutations associated with the analyzed signatures, as depicted in figures A, B, C, and D. Notably, signatures SPS 18 and SPS and ID 9 in figures B and D showed statistically significant differences, with the p-value being less than 0.05 between the groups. This provides strong evidence against the null hypothesis. On the other hand, signatures SPS 8 and SPS 39 did not show significant differences, with the p-value being greater than 0.05, providing weak evidence against the null hypothesis. Nevertheless, figures A and C revealed the presence of outliers, demonstrating an elevated frequency of somatic mutations in the childhood group. Next, regarding the sex factor, my research found that the SPS40 mutational signature in pilocytic astrocytoma was strongly associated with the female patients, with a significantly higher number of somatic mutations observed in females compared to males. At a macrocosm, my project tackled the relatively new association between the age and sex clinical features on mutational signatures in pediatric tumors. My results underscore the role of these clinical features, mutational signatures, and the need for further consideration of these features in future pediatric cancer research. My findings are a significant step towards tumorigenesis and cancer evolution in pediatric tumors. My future research will investigate how mutational signatures would be associated with the germline variants. It will be through the following stages. First, investigate the identified mutational signatures and examined factors such as the sex-specific genetic factors. I will also examine the characteristics of signatures whose etiologies are unknown. This is my hope to provide valuable insights into cancer evolution in pediatric brain tumors. Here are my references. I'm deeply grateful for Dr. Faroki at Children's Mercy Hospital. Thank you.